Hi, this is Dane Quinn from the University of Akron, and for today's video lecture, I'd like to talk about proportional damping. So this is a specific damping model that we often use for multi-degree of freedom systems. In this lecture, I want to illustrate some of the difficulties that we have when we use general damping models, which then necessitate this specific model, again known as proportional damping. We'll show in particular how proportional damping allows us to use the eigenanalysis from the undamped system and how that differs, again, from more general damping models. So let's start off and just kind of look at a general system, right? So here in the figure on the right, I have two blocks. So this is a 2-degree of freedom system. And I have a damper between blocks 1 and 2 in addition to the two springs. So here, x is going to be our coordinate vector, m is the mass matrix, c will be the damping matrix, and k will be the stiffness matrix. And for this system, in the absence of forcing, the equations of motion are given here. You can probably go and fairly easily model this using maybe momentum balance, Lagrange's equations, and these are the equations of motion that you can come up with. So how do we solve this? Well, we assume a solution. So we'll assume a solution of this form. We have a vector, sort of a mode vector, u, and an exponential rate, mu. Here, mu typically would be written as a complex number, right? So it would have real part, hopefully negative, so that the system would be stable, and maybe an imaginary component as well. So how do we use this? Well, we take the velocity given here, so that's the derivative of x. We take the second derivative of x, the acceleration, and we introduce it back into the equation of motion. So when we do that, we end up with the following. We have the mass matrix here, and then x double dot. Well, that's going to be mu squared times u, this mode vector, and e to the mu t. We'll have a damping term, so that's c times this. So that's going to be mu times u e to the mu t. And then finally the stiffness, k times u e to the mu t. And again, there's no forcing, so this will be equal to 0. Now, we can simplify this, right? So in particular, let's factor out a e to the mu t, this time-dependent part, and we're left with the following. Right, so we end up with mu squared. Mu here is this exponential rate times u plus mu times c, the damping matrix, times u, plus k times u. And then again, we factored out e to the mu t, and this has to equal 0. Now, previously, in the absence of damping, we recognize what was left as an eigenvalue problem, right? We basically had, the eigenvalue times m, u, and then we had a k and a u vector here, right? And again, we turn that into a standard eigenvalue problem. In this case, this as the eigenvalue problem is no longer familiar, right? So here we can write this as mu squared mu plus mu times c u plus k times u equals 0. And this is not a standard eigenvalue problem. So in principle, we could solve this, and we could find mu, which would be like the eigenvalues. We could find u, which would be the eigenvectors, right? But it's different. And in particular, this problem is much larger than the standard eigenvalue problem that we would have if c is equal to 0, right? So if there's no damping matrix here, then we end up with k u equals, in this case, minus mu squared m times u. And this was our generalized eigenvalue problem as written as lambda m times u. Right? So again, if there's no damping, then we think about this as just our regular eigenvalue problem. And with damping, it becomes much more difficult. Again, it's not impossible to solve, but it's not something that we typically do. So that gives rise to this idea of proportional damping. And again, it's because including a general damping term significantly increases the size of the eigenvalue problem required for the general solution. That brings us to proportional damping. This is often known as Rayleigh damping, named after Lord Rayleigh. And it takes the C matrix to be a specific form, right? So the damping matrix is written as alpha times the mass matrix plus beta times the stiffness matrix. So if we can write the damping matrix in this form, then we say that's a proportionally damped system. Here, alpha and beta are proportional damping constants. And we'll talk a little bit about those in a second. I will notice that if you look at these damping constants, alpha and beta, they have units that are a little unusual, right? So here, the unit of the damping is newtons per meters per second, right? Force divided by velocity. And so that's got to be equal to the units of alpha times the units of the mass matrix. Right? So again, units of alpha times kilograms, right? Those are the units of the mass matrix. I'll note that this quantity reduces to kilograms per second. And as a result, the units of the alpha constant are simply 1 over seconds. We can do the same for beta. The units of C, again, are newtons per meters per second. And that's got to be equal to the units of beta times the units of the stiffness matrix. And the stiffness matrix has units of newtons per meter. So the units of beta are actually just seconds. Let me remind you of the characteristic equation that we found on the previous slide. Mu squared m times u plus mu times c u plus k times u is equal to 0. So with this assumption for the damping, then that reduces to mu squared m times u plus mu, and then alpha m plus beta k times u plus k times u is equal to 0. And so we can actually combine the mass terms and the stiffness terms. And when we do that, this simplifies to mu squared plus alpha mu times the mass matrix, u, plus now mu beta plus 1 k times u is equal to 0. So really, I can write this again in our sort of standard eigenvalue form, right? And that's going to be k u is equal to, now on the other side, we'll bring this mass term, we'll actually divide by this, and we end up with minus mu squared plus alpha mu divided by 1 plus beta mu m times u. So if you look closely, this is exactly the same as the eigenvalue problem that we had in the absence of damping. The only difference is in this eigenvalue term. Right? So this would now be the eigenvalue. And if we can solve for the eigenvalue, then we can identify the appropriate value of mu, which would go then into the assumed solution here. But the important thing is that this eigenvalue problem is identical for the damped system and the undamped system. And as a result, just like we saw with modal analysis, once I've solved this, the undamped eigenvectors can be used to decouple the system into the individual modes. I mean, that was one of the real benefits of looking at the different modes of the system, was that we could treat each mode separately. If we have a proportionally damped system, then we can once again develop modal equations that decouple. So let's go and actually look and see what that kind of looks like, right? So here is our equation of motion, and I've gone ahead and put in the proportionally damped system. And for modal analysis, remember, we'll take an eigenvector, its transpose, and multiply it through. And the reason that this is convenient is because we can also write the solution as a sum of the individual modes, right? So let's say it's j is equal to from 1 to n. Maybe this is an n degree of freedom system, right? So we would write that as uj, the eigenvector, times some modal displacement, which we'll call q. So here I've written all that out just to save a little bit of time, right? So we have u transpose m times u. If you'll recall from modal analysis, if this vector and this vector are different, then this quantity would be equal to 0. So the only thing that's left is just a single term that corresponds to the ith mode, where I is what we pre-multiplied by. So if we go and identify this quantity as sort of a modal mass, right? So we'll define that as m sub I, and ui transpose k times ui as a modal stiffness, then these equations reduce to the following, right? This is obviously mi qi double dot. For the damping, we end up with alpha m plus beta k sub I times qi dot. So again, we have damping, but the coefficient of the damping depends on our proportional damping constants, as well as these modal mass and stiffness terms. And then finally, ki, qi, and this is going to be equal to, well, whatever this quantity is. So this is the modal forcing, gi. And lo and behold, each mode decouples, right? So the response of one mode is independent of all the other modes. So we can identify our frequency and damping ratio for each mode, right? So for mode I, the modal natural frequency, well, that's just k over m, right? In this case, ki divided by mi, which, recall, is u transpose times k times ui. And for the mass, right, again using this, u transpose m ui, which is actually the ith eigenvalue that we found from our eigenvalue problem. And then we can also identify a damping ratio. Right? So the damping ratio is going to be our equivalent damping, which is alpha m plus beta k. Right? Again, that's the equivalent damping for this mode, divided by 2 times the square root of equivalent stiffness times equivalent mass. Right? So ki mi. Well, we can actually simplify this and write it as alpha times m, square root of m divided by 2 square root of k, right? So I'll just take this piece, and the square root of m on the bottom cancels out with a square root of m on the top. And then plus beta, sort of similarly, we end up with the following. Well, again, square root of k over m is the modal frequency, right? So I can write this as alpha divided by 2 times omega plus beta omega divided by 2. And so we find that the damping ratio depends on the modal frequency. As well as the proportional damping constants. Right, so here I've kind of sketched these two terms. If I look at alpha over 2 omega, right, that has a dependence on the modal frequency that, basically kind of looks like this. And then this second term just scales linearly with the modal frequency. So when I add these two together, the overall damping ratio ends up looking like this, shown here in blue. Because again, this blue piece is beta omega divided by 2, and the pink curve is alpha over 2 omega. All right, so again, you add those two together, and you find your overall damping ratio. So here, if I know the proportional damping constants and I know the mode frequency, right, then that determines the damping in the system. Finally, the decay rate and the damped natural frequency can also be determined, right? And so from here, mu I is minus sigma plus I times the damped natural frequency. And in this case, sigma sub I is zeta omega, which reduces to alpha plus beta omega squared divided by 2. Right, so we see the decay rate has again a dependence on the natural frequency of each mode. And then we can calculate the damped natural frequency, omega d, right, which is just, again, omega I square root 1 minus zeta squared. And using our proportional damped constants, we can write this as omega squared minus alpha plus beta omega I squared divided by 2. And that whole thing squared. So again, with proportional damping, each mode decouples as it did for the undamped system. And I will say with general damping, right, these modes that we identify from the undamped system no longer uncouple. And it's precisely because of the general form of damping. It's only with proportionally damped systems that we once again recover this really nice property, because it allows us to look at one mode at a time. And from that, we can identify the natural frequency, which is actually the same as it was before in the absence of damping. But then we also identify the damping ratio that depends on the proportional damping constants as well as the natural frequency of the system. Right? So what this means is that in terms of the damping ratio, systems with a very low natural frequency and a very high natural frequency actually exhibit higher damping than frequencies that are in some sense in the middle. Right? And where this minimum is clearly depends on the damping present in the system. So what does it mean to be proportionally damped? Well, again, from a sort of modeling standpoint, we saw that proportional damping was proportional to both the mass and the stiffness matrix. Now, if you want to look for a physical realization of proportional damping, well, that requires some very specific assumptions for how the damping is introduced into the system. So for a mass proportional damped system, right, so here alpha is non-zero, beta, though, the coefficient multiplying k, if that vanishes, then a mass proportionally damped system, right, would look like the following. Basically, we would have damping that was between the ground and each mass. And as a result, this damping matrix for this system would be B, 0, 0, B. So we see that this is actually proportional to the mass matrix. So in this case, all masses are connected to ground with dampers. And it doesn't matter what's going on with the springs in the stiffness terms. The other requirement here is that we have a constant ratio between B, each B, and the masses that end up connecting these to the ground, right? So B can be written as alpha times M. And as a result, this C matrix, which again is B, 0, 0, B, has to be equal to alpha M, 0, 0, alpha M, which is seen to be alpha times the mass matrix. So again, if this ratio and this ratio are identical, and each mass is connected to the ground with a damper, then the system would be mass proportionally damped. So now the other part is stiffness proportional damping, and this is sometimes known as structural damping as well. In this case, each damper is parallel to a spring, right? So here we have a spring, right? So we'll have a damper in parallel. We have a spring here, so we need a damper that is parallel to that. And as a result, my damping matrix would be 2B minus B minus B and B. Right, so once again, we see that the damping matrix is now proportional to the stiffness matrix. So all stiffness and damping terms, or damping elements, occur in parallel. And we have a constant ratio between the damping coefficient and the stiffness coefficient. Right? So here B would be beta times K. Again, looking at the damping matrix, 2B minus B minus B and B. Well, with this assumption, that's going to be 2 times beta K minus beta K minus beta K, which reduces to beta times the stiffness matrix. So this would be a proportionally damped system. In general, proportional damping could contain both of these kinds of examples, right? But anything that differs from this is no longer proportionally damped. So for example, if you go back and look at that very first example that I gave here, this system is not proportionally damped because we have a stiffness and a damper in parallel, but the other spring does not have a damper in parallel with it, right? So in order to be proportionally damped, every stiffness has to have an accompanying parallel damper. And that would be an example of structural damping if it did. Or every mass would then have to be connected with a damper to ground. So again, this system is not proportionally damped. Structural damping is a very common occurrence for mechanical systems, right? Oftentimes material has both stiffness and damping properties. And over the structure, right, they may occur in parallel with constant ratio. So proportional damping is a really convenient way of introducing dissipation into multi-degree of freedom systems. It has some nice physical interpretations, and just as important, it allows us to use the undamped eigenvalue problem in order to decouple and solve for the response of the system. So that's it. Thanks so much. As always, welcome any kind of feedback you might have. Thanks a lot, and take care. Bye.